Hi, folks. Welcome. Sorry I'm a few minutes late. Sorry also for the quality of the stream yesterday. My camera in particular was quite delayed. I'm hoping it's smoother now. Shut down some of the other applications on my computer. This is probably going to be the last video I do on Arc. I'm going to cover an approach of writing Python programs using LLMs. And the reason I'm doing the live stream, other than answering questions if people have them in the chat, the reason is because I want to show how to use the repo that I've just made public. It's a repo that myself and Lewis Hemens developed to have LLMs write Python programs to try and solve Arc tasks. This approach ends up not performing very well on Arc AGI2, at least as far as we could get it. We did submit using this approach and scored 1.67%, which is lower than the 6.67 we scored post-training a TRM, a tiny recursive model, and also a lot lower than the leader, who's currently around 30%. But there kind of are a lot of things that are interesting about why this approach works well on Arc AGI1, but it doesn't work well on Arc AGI2. And there's quite a lot of tooling that we have built in order to generate data, fine-tune, run evaluation as well, that people can probably reuse. The repo is not the tidiest, although I have tidied it up a bit today. And yeah, on this video, I'm going to show you how to run some of the key commands. So at least people can watch this video and see how to run the fine tuning or how to do the evaluation. So I'm going to pull up the comments here. You can either just say hello, let me know if you have any questions. I'm on LinkedIn, X, this streaming as well on YouTube. So to get started, I'm actually going to review the SOAR paper. SOAR is a paper that came out last year, well, no, earlier this year, that uses LLMs to write Python programs. Not only does it use LLMs, it fine-tunes the LLMs to try and improve the performance and shows that the performance improves. It's able to score over 50% on Arc AGI1 evaluation tasks, which is higher than the winner last year, or roughly in the same vicinity. And so Lewis and I, when we started off competing in this year's prize, our thought was, well, what if we take the SOAR approach from Arc AGI1 and just apply that to Arc AGI2? Now, to apply the approach, we needed a data set of programs. So we started using the strongest LLMs out there, which was before Grok 4, actually, just a few months ago. We used those to generate Python programs and generate data sets containing programs that solve Arc training tasks. And then we fine-tuned a model, a Qwen 4B model and 8B. We also tried tuning OSS. And then we would evaluate the model on Arc AGI2 evaluation tasks. So in this video, I'm going to describe the SOAR paper by Julien and his co-authors. Julien also took some time, which was appreciated, to talk with Lewis and I, and also shared some of the data that we used to pull together a larger data set of programs that we've now put on Hugging Face. So I'm going to go through the paper fairly fast, and then I want to go through evaluating, running this whole strategy using any LLM, either a private LLM or one that's on Hugging Face. I'll show you a pretty easy way to do that. And then I want to show you how we ran the fine tuning. I'll go through the fine tuning script. So hopefully by the end, you should have the tools for running this approach and improving on it. I'll also spend a tiny bit of time showing a tool I've vibe coded at the end that allows you to make your own Arc tasks. I suspect this is maybe underappreciated, actually trying to write your own tasks, not just because you learn more about Arc by writing tasks, but potentially because the data set is so small, maybe if we spent more time as researchers trying to write the tasks, it might just lead to either having some expanded data or more insights around how we might go about solving Arc as a whole. So let me share my screen and kick off by showing the paper. This is the repo I'm going to share. Well, it's already public. It's Trellis Research on GitHub, arc-agi-2025. But first, let's take a look at the paper here. And before I go into explaining the curves, this is really the key graph I'm going to focus on. Let me just briefly show you an example of what a prompt looks like. This is the prompt here, and the prompt that Lewis and I use is not that different. In fact, we ended up just mirroring it so we could replicate performance of the paper. So you're an AI assistant specialized in solving ARC reasoning corpus tasks. Your goal is to analyze input-output grid pairs, which are shown here. The outputs were produced by applying a transformation rule to the inputs. Implement the transformation rule as a Python function. So you're feeding in this brief description. The SOAR paper decides to attribute colors to the numbers, which is not necessary, but you can do it. And then the LLM is tasked with taking in these grids specified in this format and then providing a Python program. Now, SOAR goes beyond this and does what has become known as refinement. I should say, by the way, this type of approach probably was tried by many people, but probably the canonical example is Ryan Greenblatt's blog from last year when he used GPT-4o to write a lot of programs. And that performed, I think, over 50% on ArcAGI 1. And Ryan Greenblatt also used refinement. What is refinement? Refinement means taking a program. Let's see if there is a program here. Does it give an example? Just gives input grids. Yeah, taking a program, which is denoted previous implementation, and then trying to fix the program. So like the prompt I showed above, you still pass in the input grids, but you also pass in a previous attempt that did not get the outputs correct, the train outputs correct. And you ask the LLM to try and fix the program. So that's what we'll call, and is typically called in literature, refinement. I should say that when you run this approach, it's very important that you sample many times. So you don't just generate one program per task. You get the LLM at a temperature of 1, perhaps, to generate many, many programs. And then you execute the programs on the training examples. So say you have 3 training examples, and the examples are example pairs with an input and output. You run the program on each of the 3 inputs, and it's going to give an output, and you'll compare that output to the input, or sorry, to the ground truth. And if they are correct, that gives you a signal that the program will hopefully generalize, and you can roll it forward on the test input to make the actual prediction that you submit. But in doing this, it's critical that to get good performance, we'll see it in the graphs, you run the program, you run the LLM many times to get many programs per task. And as you sample more and you do majority voting, so you will upweight the programs that give similar outputs. If you get many of the similar outputs many times, you'll upweight that with majority voting. And when you do this, your performance improves roughly with the logarithm of sampling. Now, it does asymptote, but sampling is the biggest driver of performance in this overall approach. I can't overemphasize that enough. You'll see that in a model that's not fine-tuned, but you'll also see it in models that are fine-tuned. Okay, so I've shown you the prompts, and now I'm going to show you the performance. And there's a few layers to how this approach is rolled out. Sorry, here we go. So the SOAR paper trains a few models, Qwen 2.5. Qwen 3 wasn't out at that time. Qwen 3 was out when Lewis and I did our work, so we used Qwen 3. The SOAR paper looks at different model sizes, 7B, 14B, 32B, 72B, and then Mistral Large, which is 123B. So it looks as a pretty wide range of models. The bigger models perform better, although not that much better. You can see Mistral Large gets up to 45% here, but already you're at roughly that with Qwen 2.5 Coder 32B, and you're not that far off of it, even at the 14B scale. Now you are below it at the 7B scale. We found on Qwen 3 that you get a lot of good performance even at the 4B scale. So yeah, size improves performance if you have a bigger model, but it does seem to kind of hit some kind of a plateau. Now, there are 4 curves shown here, and I'm going to talk through each of them. I'm going to zoom in. Okay. Now, I'm going to turn down the music a little bit, actually, because that can be annoying. And maybe somebody let me know in the chat if the video quality is a bit better than yesterday. Maybe somebody was on yesterday. All right, so on the x-axis, we have the number of samples in base 2, so 2, 8, 32. On the y-axis, we have ARC test score. Confusingly, this is the ARC evaluation, ARC prize 1, so last year's competition, evaluation set, which has 400 tasks in it. They use the word test, but it's really evaluation. And we'll start with this gray curve at the bottom. Basically, if you take a Qwen 2.5 Coder 7B model off the shelf, and indeed if you take a 14B model off the shelf as well, it will score very low. on the evaluation set. No pre-training involved here. We're just sampling. But as you sample and sample and sample, if you start to sample 3,000 times, your majority score. Oh, you don't see the screen. You're right, Simon. Sorry. Here we go. I'll say this again. So on the x-axis here, we've got the number of samples, base 2. On the y-axis, we've got the evaluation score. On the ARC price 1 dataset evaluation split, 400 tasks. And what I said was the gray line here indicates that if you take a raw model off the shelf, and this is not a reasoning model, it will score pretty much 0 until you get to large samples. If you sample 3,000 times about here, you'll get to just under 10%, about 8%. And then if you additionally add refinement, which means taking the wrong programs and refining them into better programs, you can boost that even more and get up here to maybe around 15%. So just by doing lots of sampling, you can actually get some correct programs, at least on the ARC AGI1 tasks. So then the SOAR paper goes further, and it takes these 6,000 programs. It takes some of the better programs, although it ablates different splits of those, and uses those programs to fine-tune the model. And that fine-tuned model is what we see here in yellow. Now, this is a bit misleading, and I talk about this in the blog, where you can find it on Substack, trellis.substack.com. I talk about all of our approaches here around writing Python programs. The yellow curve corresponds to training on the same number of examples. Now, you might think, oh, lower number of samples left here, but this is the number of inference samples. It's not the number of training samples. All points on this yellow curve have been trained with a data set drawing from the 6,000, 3,000 samples and 3,000 refinements. And so what the yellow curve shows you is after you fine-tuned, this is what the sampling curve now moves to. It moves up significantly. So now you're able to get up to a score after just 3,000 samples of this of about 26.7, and you can get up to about 33 here. So this is with one iteration of training. Now, it's actually a little bit more nuanced than that, because right here, what I showed you was the curve. Well, what I'm showing you is a plot for Qwen Coder 7b, but actually the data set that it's being drawn from is all of the data generated. So it's the data generated not just from this small model, but actually all of the models here, which is a lot more powerful because you're getting the benefit of the bigger models. So you can imagine sampling from all of these models and then using that data, sampling from that, taking from that the best rows in order to fine tune. That's what this corresponds to when it says all train. Now, of course, it would be interesting to just look at the own models generations and tune on that, and there are graphs showing that. But here it's the all train. So we're using all of the data generated in sampling to then train, or to pull a subset for training. Okay, so the idea is you do this training loop, and now you do what's called a test time loop. And in the test time loop, you take the test examples, which are really evaluation split examples, and you take from that the train examples. So in ARC, you have train examples in a task, and you have test examples. And the train examples will show you inputs and outputs, and the test examples will just show you the inputs. What you do for test time tuning is you take the train examples and you sample those to try and generate programs that will produce the outputs. And when you generate that set of programs, you use it for fine tuning. So we have pre-training on a training split of tasks, and that gets us to the yellow curve. And then we have test time tuning, which can bring us then to the red curve here, where we are training during the competition, if you're thinking about Kaggle, and we are training on the train examples from the evaluation split. And then we roll forward and we evaluate performance on the test outputs. And if you iterate that again, you get to the final curve. Now you can see diminishing returns. So you get the performance improves a little bit more here. So this is the idea of writing Python programs. You try with a base model, loads of sampling. You can improve on that by fine tuning the base model. You can further improve on that by doing some test time tuning during the competition, for example. So I'm going to show you the scripts for doing the fine tuning. First, I'll show you the scripts for doing the evaluation, and I'll talk a bit about that. Now, I'm not going to focus too much on this because it's written in the blog, but it turns out that the test time tuning is not nearly as useful as you think it is when you are in a compute constrained environment. Basically, a lot of this improvement you get from going from yellow up to red here is simply because the authors have test time tuned on a corpus of 6,000 samples per model. So they're taking 6,000 samples that have been generated with the trained model, and then they're picking a selection of those to do the test time tuning. The problem is, in a Kaggle notebook during the competition, you're not going to be able to generate 6,000 samples. You're going to be able to generate way less samples than that. And so the boost that you get in test time performance is going to be pretty small. And moreover, you're not even going to be able to do sampling at a level of 3,000 or 6,000. And so there's this trade-off between, should I keep sampling and trying to work my way up this curve? Actually, the best way to look at this is, you're on this yellow curve because you've got a pre-trained model. You arrive into Kaggle with the pre-trained model, and you say, okay, I'm going to start walking up this yellow curve here. So I'm going to sample and sample and sample. And now, do I want to start doing refinement? And the way I decide whether it's worth doing refinement is if the slope of the curve for refinement is higher or becomes higher than my slope for just sampling more. Because if my slope for sampling is higher, I should just keep on sampling and use the compute for sampling. Now, the slopes here are not visually, they're not giving you the right message because we're on log plot here. But if you plotted this linearly, and then you compared the slope, say, of sampling here versus the refinement slope, you could make a decision on whether you should actually bother refining. And basically what you conclude is that you should probably just continue sampling, and you won't even get into the regime where the refinement helps. And it's analogous in the case of doing test time tuning. You can decide, I want to expend compute on test time tuning, which is going to boost my model up a little bit. But it turns out that you're probably better off continuing to sample more, because the slope of the curve for test time tuning is, or for sampling, is probably better than deciding to go into the test time tuning mode. So that's a really key thing that was not instructive. We thought at the start of the competition, right, we're going to train a really good pre-trained model. We're going to get in there, do some inference, generate some samples, do some test time tuning, and then do some great inference that will improve our score. But when we actually did that, you get basically no improvement with the test time tuning. You're better off just sampling for the whole 12 hours of the Kaggle competition that you get. So that's the SOAR paper. I see a question here. What's the name of the paper? It's called SOAR. Sorry, I'm in the paper, so I just need to scroll up. Let me zoom out. And it's called Self-Improving Language Models for Evolutionary Program Synthesis by Julien, Cédric, and Pierre-Yves. Very nicely written paper, and it shows up some nice ablations as well. So now I'm going to show you how to implement this. And by the way, there is a repo that's public. Julien's made public. He's also made public the models that he's trained and the data set. And the data set was really helpful in kickstarting the data set that Lewis and I put together, which is for ArcAGI2. We did build a repo from scratch, though, and that's the repo that I'm going to show you today. But actually, first, I want to show you the data set that we pulled together and some of the stats. Just give me a second, and I'm going to pull that up. But I want to show you how hard it was to get data for ArcAGI2. And this is a big reason why I think we weren't able to do very well by taking this approach, and ultimately why we pivoted to a different approach. So I'm just going to, I'm going to Looker Studio, because I should be able to find. Sorry, bear with me. Okay, I have it here. Now I'm going to share my screen. So here we have the stats of the data sets that we pulled together, which are built on the programs that Julien had put together. And it's probably helpful if I just show you in Hugging Face first what these data sets of programs look like. And I can do that just by going to one of these data sets that we've open sourced. So a pre-training data set, or test time tuning, if you wanted to do that, involves a task ID. So this is an arc task, optionally some reasoning if we've collected a reasoning trace, some code, then the predicted train output, the predicted test outputs. This is an array of the grids. So an array will have multiple grids for each training example and for each test output, the model that was used to generate the program. And there's also this flag here is transductive, which I'll talk about in a second. What else? There is also information on which training examples this program gets correct and which test examples this program gets correct. So the paper will actually fine tune not just on fully correct programs, but also on partially correct that might get 1 or 2 train examples correct, and even sometimes on incorrect programs. Now, it makes no sense to train on a program that is incorrect and train it on, yeah, like matching an incorrect program with correct outputs, that's just going to mess up the model. So if you want to use a partially correct program or fully incorrect program, you need to relabel the outputs. So if you have input grids and you have ground truth output grids, you need to swap the ground truth output grids for fine tuning on incorrect examples. You need to swap them with what the program actually generates. Now, there's a whole question of, is it even worth it to train on partially correct programs or incorrect programs? Generally, I think we are skeptical, just because when we manually inspect partially correct or incorrect programs, they don't really look, the outputs don't necessarily look like what we would consider ARC tasks. But Julien does ablate this, but there's very small differences in performance. So it's kind of hard to know. That's a bit of a sidebar, but this is the data set. And I want to show you the stats now. So here we have ARC Prize 2024 training. There are 400 tasks. And of those 400, we have programs that are fully correct on 362 of those tasks. Now, there's actually a Kaggle competition that's separate just to write programs for this specific data set. And the competition is to write the programs to be as short as possible. And I believe people have either written manually or with the help of AI, written short programs for this. I believe also that there's an ARC data set by Michael Hodel, who also manually wrote solutions to all of these tasks. But suffice to say, we have good coverage. So we have programs that solve pretty much all of the training split. But if you move then to the evaluation split, and this is including after we use strong models like GPT-5 and Google Flash and Google Pro, we have pretty poor coverage on even ArcAGI-1 dataset. We've got 283 out of 400 tasks that are fully solved. And it gets even worse then when we move to the ArcAGI-2 dataset. Here on the training set of 1,000, we've only 722. And actually, a lot of the ARC Prize 25 training set is just the evaluation and training splits from 2024. There's really only about 200 and something new tasks in the 25 training set. And if you split out the hard tasks in the 25 training set, which we did by giving GPT-5 Mini 8 attempts to solve them, and if GPT-5 Mini did not solve them, we consider them training hard. So there are 137 of those. And here we've only got 50 fully correct. And then even worse, on the evaluation tasks from 2025, out of 120, we've only got 6 that are fully correct. So a pretty simple guess for why this whole approach of trying to do SOAR, the Python program writing with fine tuning on this year's competition, one simple guess why we failed at that is because we just had really poor data. We had really poor data, so we weren't really able to hill climb at all. And that's probably a big explainer for why we only got 1.67%. So yeah, we spent $2,000 or $3,000 through OpenRouter with some of the strongest models to generate programs. And we have pushed them up. So you can check out, there's a collection, I've linked it in the blog, but there's a collection of 3 different data sets where you can find some of the programs that we pushed up. Some all correct, partially correct. I think it's mostly all correct and partially correct. There's some fully incorrect, but we think the value is mostly in the all correct ones. So that's a quick insight into the data set and why this was overall challenging. But I'm going to move now to show you how to generate these programs, how to generate them with strong language models like GPT-5 or even Grok, how to generate them using a model from Hugging Face by spinning up a runpod instance. These are all one-line commands, so they're fairly straightforward. And then I'll walk through the fine-tuning script. So let's see if we can do that. What I'll do to start is, well, I've done this already, but I've cloned this repo, ArcAGI-2025 on Trellis Research. I have it in VS Code. Yes, I've gone back to VS Code, having spent time on Windsurf, Cursor, Claude, Now I'm using Codex and Claude a bit. So you'll find a README that describes how to get this repo set up. And it's all set up using UV. It also can be run on RunPod if you want to do fine tuning, which is something we're going to do later. But you can run commands just from the repo locally on your laptop, especially if you're calling a service for doing inference, or even you're trying to spin up RunPod instances for evaluation. We've set things up so that you can issue a command if you set a RunPod API key. So I recommend in a .env file in root, you need to add in, well, two things depending on what you want to do. One is add in a RunPod API key if you want to be able to spin up pods, or set an OpenAI API key. And actually, it shouldn't be _OpenAI. It should just be OpenAI API key. I'm going to push that there. Fix API key name for OpenAI. And if you set that, I've currently set this in my .env file as my OpenRouter API key. That will allow me to make requests via OpenRouter. So just going to push up those changes. Okay, so what I want to show you is how to generate Python programs and evaluate performance using a model that's on OpenRouter. And then I want to show you how to do that using a model that is spun up from Hugging Face. And yeah, that typically would be a base model, or a model that you fine-tuned. So let me increase my screen a little bit, close this off. And first thing we're going to do is we're going to evaluate using GPT-5 Nano. So I want to see how it's going to perform on the 2025 data set. I want to see how it's going to do on the evaluation split. Because we've limited time here together, I'm going to just look at the first 10 tasks. If you didn't pass this argument, it would run through all 400. I'm going to parallelize inference. So I'm going to have 64 workers. And they're workers that are parallel for two purposes. It means I'm hitting OpenRouter with 64 parallel requests, but it also means that I'm executing the programs in an execution environment in parallel. And yeah, this speeds things up a lot. Now, one of the big challenges of the Python writing approach is actually executing Python programs. You don't know which ones are bad and are going to blow up your memory. And it's a lot harder than we expected to manage that and not have random crashes during the script. That resulted in a lot of submission crashes and a lot of evaluation crashes. And I don't think we even at the end had a confident way to completely avoid. We would try and cap the amount of memory that any given worker could use, but sometimes it just blasts through the cap so fast that you don't shut it down on time. It's actually quite a difficult problem that Eric Peng as well, when he was doing Python writing with Grok 4, he highlighted how it's just not easy to do evaluation. There is the option, if you don't pass unsafe executor, it'll execute in Docker. You need to have Docker running for that to work. I'm going to take the risk here, so it'll run on my computer. And I'm going to assign a maximum number of attempts. So if you want to give the model more attempts, I mean, let's just give it 4. Typically, this needs to be a large number. If you're using a model you're pre-training, you're going to want it to be 64, 128. In the competition, you're going to want it to be as large as possible that you can run within the 12 hours. And then there's a max tokens parameter. So these programs these requests to the LLMs are just requesting programs. I'm not including reasoning, and there's no chain of thought or anything. The models are just being trained to directly output a program. So max tokens of 3,200 is too large if you're using a base model that's just directly predicting. But if you're using a model like GPT-5 Nano, which actually does have reasoning, then you need to have a larger max tokens. You probably need at least 16,000 for that. And you might even need 64 if you wanted GPT-5 or even 128. And obviously that gets really expensive and it gets slow as well for doing everything. So let's run this here. By the way, if you just want to figure out what flags are available, you can just paste in the command with .h. So I'll show you that now. So just in the bottom, -h, and it should come up with a list of the arguments that I can use. I'm not going to have time to go through everything here. By default, it will log to a data set and the name will be chosen automatically. You can customize that. You can customize the reasoning effort. You can customize the base URL. So you can use this command with any OpenAI OpenAI style endpoint. Literally, you could use OpenAI, you could use Google, they accept OpenAI. You could use any other service. I'm using OpenRouter, as you can see here. And you have to pick the model so that it matches, the model name needs to match what the API vendor is using. You can customize temperature. What else is worth highlighting? You can also do refinement. So you can, if you want to do refinement, you need to pass in a data set of programs. So you need to pass in that data set. You can pass it in as Hugging Face or as a Parquet format. There's also early stopping threshold. So this is designed to save compute if the program, if threshold number, I think it's 7 programs are found to get everything correct, all the train examples correct, it's going to stop sampling. So this is a heuristic so that you don't just keep sampling and keep using up compute, even if you solved an easy problem. All right, so let's run this and see what it comes up with. Okay, so first thing it does is it prints out the system message, it prints out the prompt, which we've already gone through. Then it prints out all of the input and outputs for the train examples, and then it prints the inputs for the test examples. And it's saying here that it's starting 40 attempts with 64 workers. And yeah, basically there's 10, we're limiting it to 10 tasks and 4 attempts each. So it's not going to be able to use all the 64 workers. It's only going to use 40. And it's now going to hit the endpoint. The reason it says LLM metrics fetch failed is because if you were hitting runpod with SGLang, it's going to give you the SGLang metrics, which we'll see in a moment. But if you're just hitting a private endpoint, then it's not usually going to respond with metrics. Now, the other thing, I'll just let that run in the background. But what I'll show you now is how you can run an arbitrary model from Hugging Face. And the model I'm going to run is the one that scored 1.67% in the competition. It's a model that actually was trained in the SOAR paper. And I then just converted it into an FP8 model using LLM compressor. By going to FP8, you can multiply inference speed by about 1.6 maybe on an L4 Lovelace architecture. By default, also the models will run with FP8 KV cache, which also gives a speed up of about 1.5 to 2. So the FP8 speed up is fairly significant. But you can find this model. It's now open source here. I mean, the model was always open source, the SOAR Quen 14b. And yeah, it comes from the original model there. So we can run this. You can run it in the background if you like, using Python unbuffered and NoHub. And you can send the logs to a log file, but I'm just going to run it like this here. Let's not run 64 attempts. Let's just run, well, actually, these attempts are really fast because there's no reasoning. So the number of tokens that need to be generated is quite small. So any of these requests will run, unlike GPT-5 Nano, which is reasoning, and it'll take quite a while for each request. These requests are really fast. So here I'm going to run create pod and run tasks, which is going to boot up a run pod H100. And once it's booted up, it's going to check the endpoint is at, I mean, why don't I just get it going? Then I can talk about it. So paste it in here. All right. So I'll just talk through. It's loaded a template for SGLang. It's creating a pod with this model here. You can optionally run it on multiple GPUs in parallel if you want to speed up inference. It's using this FP8 E4M3, so exponent 4 Mantissa 3 type FP8. There's also exponent 5 Mantissa 2 is another common one. It probably would perform well too. It creates the pod, and now we're waiting for the pod to be ready. Once the pod is ready, it's then going to get SGLang going. Once SGLang is going and we hit it with a few practice requests, then it will start the evaluation script. So it's going to evaluate our model on the evaluation split of this ArcAGI1 training set. All right, so you can see that we've started to make progress here on the GPT-5 Nano model. It's taking a few minutes before we even have any requests that return. Well, some of them are returning here and done. As we have a complete task, which means all of the attempts have returned 4 attempts, it will then print the stats. So this task here, which it's always easy if you go to arcprize.org and you then go to play, you can just go to the URL and, well, pick a task first, like this, and then you can substitute in the task ID and see what the task is. So this is the task that it is trying to solve, and it looks like some kind of a path joining task where it's like bouncing between the objects. And this task has not been passed for them, or test incorrect, for train incorrect. So basically got all of that wrong. We can move down to see some others, see if there's any that it gets correct. Let's see. So here's a task where in the 4 attempts, it's got 4 tests incorrect, 1 train perfect, which means it gets all of the training examples right. 2 train partial, that means it gets 2 attempts where it's got at least 1 of the grids correct. And I'm going to explain what this transductive thing is, which is a rabbit hole that we went down. So when you have a program, ideally it's something like flip, rotate from inputs to outputs. But the LLM will sometimes give a trivial program that for every input grid will give the output grid. So we'll just hard code the output grid depending on what the input grid is, which is absolutely not what you want, because that will give the correct answers for the training grids, but it will be wrong for the test grids. The SOAR paper tries to mitigate this by looking for exact matches of the output grids inside the programs. And this is good because it pulls those out. But the LLMs are sometimes more nuanced in how they'll do this hard coding. And they will have hard coding on a row by row basis or column by column basis, which is still transductive or cheating in that it's not really a general transformation. It's a one-to-one mapping. And you really don't want to train on that. And you probably don't want to include it in voting. So how do you detect those? We looked at using embeddings models. They don't work. We looked at even using LLMs, not very robust either. In the end, Lewis came up with a pattern, well, a feature-based model. Features like the number of new lines, the number of times certain variables appear. He engineered, I think, about 40 features. And using that, the regressions on those features, we were able to get a model that had a reasonable, what's it called? F1 score, a reasonable recognition score on whether a program was transductive or not. So that's why you see transductive appearing. We typically will drop those from training, but we will include them at a lower weighting in the voting, because sometimes they can actually solve the tasks in the same way a transductive model would if they provide a mapping for the test output grid that's correct, but generally they don't. So you want to penalize them. Okay, that was a bit of a sidebar. So let's see how we're doing. The pod is actually still initializing. If I go over to run pod, I can probably see it. So you can see here a fine-tuning pod that we're going to talk about now. You can also see this SGLang pod SOAR Quen 14B FP8 dynamic. And if we look at the pod here, you can see it's an SGLang launch command. It's going to run on port 8080 with this model here, data parallel 1, and here's the KV cache type. So that's still initializing. If I check logs, probably the container is still downloading. In a second, it will pop up here with the containers logs, and it will start to show SGLang booting up. Okay, yeah. So now SGLang has to install, and then it has to boot up, and then we're going to run the inference. So we'll come back to that. With this, you should now be able to run evaluation on any model from any endpoint that supports OpenAI style endpoints. You should also be able to run a custom model that can be inferenced using SGLang. So the next thing to show you is fine tuning, which is relevant for pre-training. It's technically relevant as well for test time tuning, but as I explained earlier in the live stream, test time tuning is not useful if you're compute constrained. Maybe we're missing something. Maybe there's some way that you get insane improvement from test time tuning, but basically what we find is that if you've limited compute, you should use that compute for sampling, probably not use it for refinement or not use it for doing test time training. Just one other comment on test time training, and I'll do it by looking at the graph that we originally looked at. When you sample a model, you're moving up a curve, this yellow curve here. This is when you increasingly sample a pre-trained model. So you want to go as far to the right here as possible as compute allows you to. When you then take those samples, so let's say you stop here at 2 2E5 or 2E7, 128. If you stop here and use those samples to fine tune, which by the way is not a lot of samples, what you will achieve with that fine tuning typically is, with the fine tuned version of that model, you will now, with fewer samples, be able to achieve closer to that performance. So whereas with an unfine tuned, and I mean untest time fine tuned model, you can get to here, if you now fine tune it, you may be able to get to that same point of 18, but with fewer samples. So fine tuning it builds rare correct examples into more common correct examples. That's the primary effect of fine tuning. You would like fine tuning to do more. Really, you would like fine tuning to somehow hill climb and actually increase what you might think of as your pass at 128 or your pass at 1000 performance. So you would really like your fine tuning to improve, to find more rare examples. That's what you would really like, is not just to make the rare examples more common, but to find rare examples you didn't find before. That's ultimately what machine learning is all talking about today. Hill climbing, reinforcement learning, that's the holy grail. But a lot of the time when you do fine tuning or reinforcement learning, you don't hill climb, you don't find more rare examples, you just make the rare examples more common, which is good because it's more efficient then when you do a future inference. But if you're in test time tuning, you've already spent the compute to do the inference. You have those answers, you have the rare answers. Just by fine tuning and making them more common is now a waste of time because you already have the answers. It is useful in pre-training because you can basically amortize, well, not amortize, but you can use lots of compute before the competition, make the rare answers common, and then during the competition you now have a model that will more commonly provide those difficult answers. And that's good because you're saving compute at competition time. But at competition time, you just want to sample. Compacting that knowledge back to be more common is not going to be useful. Okay, so let's talk about fine tuning. And for that, we need to go back to VS Code and we will go up to the top. Well, actually go to the next section that explains how to do fine tuning. So fine tuning I recommend doing in a Jupyter notebook. There is a script that will convert the notebook into a script, so you can run it from command line, and that's what we did when we did test time tuning. But if you're just going to run pre-training, it's a lot easier to look at it in a notebook. Lewis might disagree. He loves running stuff from notebooks and from scripts, not notebooks. And I can see his point. Fair enough. The easiest way to go is to use this one-click template. It is an affiliate link, and it is only for RunPod. You could do the same on another service if you follow the installation instructions here for UV. But if you want all of that automated, you can use this one-click template, which I've just clicked. And we would fine tune on the largest possible GPU, which allows us to use a larger batch size. So we would use often a B200. But yeah, probably some of these are good on a compute value basis, and yeah, fine tuning. I think technically I have adapted the script so you can avoid using Onslaught and use transformers and maybe get a better multi-GPU experience. In principle, you can do Onslaught on data parallel, which is what you want to do here, or you can do here because the model is not that big. I have a video. If you look on Trellis Research YouTube channel, you can find the DDP video that will explain how to do that. This script is not quite set up for that because I don't think I got to that point. So we did most of our fine tuning on single GPU, and typically it would be about 8 hours to 24 to 48 hours for the longest runs on 100 rows of data. So yeah, I'd select one GPU and get it running. And once it's running, which I did this earlier, you go over to, well, click on the pod, go to the HTTP service, and it should boot up. It should boot up Jupyter, which I actually already have running over here. Now, once you're in Jupyter, you should find yourself in the ArcAGI 2025 folder, and you will automatically be on the main branch, which is correct. Go to LLM Python, go then to fine tuning, and then open up the Onslaught Arc fine tuning notebook, which I have right here. Now, everything should be installed because of how the RunPod template is set up. If you're trying to tune Onslaught or OSS with Onslaught, you do need to make some upgrades. Eventually, I guess you won't need to because they'll be built into PyPy, and maybe they even are already. But if you want to be sure, you can do that. So at this point, you can just run the full script, but first it's best to check the config file, which is setting up your fine tuning. And I'll talk through these parameters here. So first parameter here is test run. I recommend always doing this first, set it to true. What it does is it will just run with 128 rows of data. And this allows you to run the data prep, the validation, the fine tuning, and pushing models to hub. You can check that everything works before you go off on doing a full run. So actually, let's set that to true. Data. So you can load from a Hugging Face or a Parquet file. If you want to use Parquet, use Cloud Code or Codex to talk with the repo and figure out the format for Parquets and how we make them. There are tools for making them. Because we're using Hugging Face, we will point to a data set. I've made 3 data sets public. You can find them if you go to Trellis and then look at collections, ArcAGI Python programs. There's that FP8 dynamic model, and then there are 3 data sets. There's a smallish data set that includes reasoning traces. You can technically train on the reasoning traces. We did not find that this works well. In principle, maybe it works with a lot more data plus a stronger base model. Unfortunately, the OSS model is quite unstable when you give it long prompts, and it doesn't generate sensible output. This, I think, is a known problem by now with OSS models, especially with the 20B one as opposed to the 120B. In principle, you could fit 120B on 4x4, but the number of samples you would get per task is so low that it's not going to be useful. So realistically, the strongest in theory model at the time was probably OSS 20B, but it had stability problems when you run it for reasoning. So yeah, that's kind of an issue. The other thing that's an issue is, even though it's very fast because it's a mixture of experts and activates very few parameters, the problem is that any reasoning model has to generate a ton of tokens. And so each token might be fast, but if you're generating 60,000 of them compared to generating only about 1,000 for a program only, that's kind of an average length of the programs. It just takes so long to use a reasoning model. And it's going to be hard to have enough sampling to do well on the benchmark. So anyway, we've provided a small data set with some reasoning. We've also provided some much bigger data sets. The biggest data set is ArcAGI2 all 100, which has got pretty much it's got all correct tasks from our data set here, along with some partially correct tasks. This probably would take about 48 hours or maybe a bit longer if you want to train on this. I can feed this in because we're only going to load a few examples, but just so that things run fast, I'm going to train on this ArcAGI2 reasoning data set. I'm not going to use the reasoning though. I'm going to turn that off, but I've specified the data set here. And actually the reasoning, you'll see it down here. Enable thinking is set to false, and you have to set that true to include thinking traces. Execution mode. So there's 2 ways to do this. You can fine tune, and full means that it's going to save intermediate checkpoints and push them to hub, which is good for if you're doing a long run, or you can just save the final checkpoint, which is more lightweight and maybe good for test mode. In fact, yeah, that's it. Next is the model. We're just going to train Qwen 3.4b, which was the strongest model at the time before OSS came out. Well, not this size, but the Qwen 3 family. You can train in 4-bit. Typically, I avoid that if I don't have to, just because it does hit performance a little bit. The max length needs to be set longer than the total length of the prompt plus response. We're going to see printout for that. LoRa rank, we are doing LoRa fine-tuning, not full fine-tuning. You can probably set this to 16. I don't know. You could even maybe set it to 1 and it works to some degree. We didn't ablate it, but the memory is not so high anyway that you have to go down that low. We're going to use unsloth. We're going to evaluate, and we're going to set the batch size to 4. You should set the batch size large enough to use the CUDA cores. And the way you know that is by checking the telemetry of the pod. So you would go to telemetry and see. It looks like I have the model loaded from earlier. During training, this will go up a bit. But if it doesn't go up, too high, you can maybe increase the batch size. I think you can probably go with 8 for this 4B model, and it's batch size per device. Normally you set this globally, but I actually think it makes more sense to set it on a per device basis, because if you then decide you want to run on 8 devices, what stays constant is the per device. It's not the global batch size. Anyway, just maybe some other reason why people like setting global batch size. I guess global batch size does have to do with the learning rate dynamics. That's the learning rate you use is associated with the global batch size. So I guess that's maybe why setting global batch size is more common. And let's see, per the batch size, effective batch size, fusing, yeah. Gradient accumulation. Yeah, that might be misleading actually how that's labeled. So I'd have to go back and check that in the code. Okay, and then the overrides, this is the max test rows. Yeah, you can actually, this is not good. If I have it in test mode, it's not going to run for 128. It's going to run for whatever I specify here. If this was null, it would do 128, I think. But it's actually going to use only 32 rows. So I could set that to 128 maybe. Okay, so my configuration is set. And with that, I'm going to kill this kernel. So let's shut down all kernels. And I'll have to reselect it here maybe. Sometimes you might find that the notebook fails, and that's because you have not selected the kernel that all of the installs happened in. This is set up in the onStart command in runpod. All right, so I'm going to do run all cells, which brings me to the bottom of the notebook. It'll confirm the versions of unsloth. It's now going to load the YAML file, so it's just loading up that config. We're going to report to weights and biases, and now it's going to load the model. So we should see the model popping up here, loaded by unsloth. I should have said, when you have one GPU with unsloth, it's the same speed as 2 GPUs with transformers. So actually, to get the benefit from multiple GPUs, you need to have more than 2 GPUs. Otherwise you're not getting any speed up. Now, unsloth does actually support data parallel. So if you use unsloth in data parallel, and you would need to watch the video, then you can, with 2 GPUs or more GPUs, still use unsloth. So you get the 2x speed up from unsloth, plus you get whatever speed up from using multiple GPUs. All right. So the model is going to take a second to load up. Shouldn't be that long because I downloaded it earlier, and it's a small model, so the shards should load fast. Then we're going to apply LoRa to these modules here. After applying LoRa, we're going to do some data preparation. The data is fairly clean because Lewis has scripts that cleaned it up, but there are things you want to do with the code, like decide whether you want to include comments or not. You probably don't want double new lines anywhere. So any double new lines you probably want to remove. Any random extra spaces you probably want to remove. So we run a series of checks. You're going to see a series of checks. And we're also going to run some executions. So we will take the data, execute it, check that the outputs actually match what's in the raw data set. So we run a series of checks like that, which in principle you don't need if you prepared your data set well, but it's always easy in data prep to make mistakes. So it's nice to have a double set of checks, which we have here in this notebook. So hopefully these will all run once the model is loaded. Okay, checkpoint shards are loaded. It says the attention is eager, but actually unsloth is using its own attention internally. So don't worry that it's going to be using too much memory. As long as you're on the latest version of unsloth, that should work fine. All right, so we're now going to go through data prep. Here's an example of code cleaning. It'll just remove extra lines. You can see here, for example, it's gotten rid of a double U line here. Now it's going to start to map them into the format we need. Okay, reasoning is none. Yeah, well, that's because we turned off reasoning. It's giving this warning. We have a data set where there's reasoning available, but we're not using it. And we now have the train and validation split. The validation split is always going to be the max of 10% of the data set, or 32 rows. You can configure that as well. And we should see the statistics here. So the maximum, the median length of the train set is 11446. The max is 4424. That's because we're only looking at the first 128 rows. But if you look at more, the max is actually closer to 19,000. So you do need to have a model length of at least 20,000. And by the way, most of those tokens are not the program. The program's 1 to 2,000. It's really long examples because some of the tasks have got even 10 training pairs. And some of the tasks have grids that are 30 by 30, so they can be quite long. This is the integrity tests. So we run through a battery of integrity tests, check that the outputs actually match ground truth. Look at those results. Looks like we've passed all the integrity tests here. And with that, you can examine the failures. We haven't failed anything, so you can examine a certain index here, but we haven't failed anything, so there's nothing to really examine. And now we are ready to move on basically to training. Now there's some subtlety here. I'm not going to go through in too much detail, but you basically want to train, you want the loss to be focused on the program and or the reasoning. If you've got a reasoning trace, you want it to be on the reasoning and the program, but you don't want to focus the loss on the whole question. So you need to do this kind of masking. And the masking will depend on the model, which it depends on the chat template, which depends on the model. So you need to pick the right template. Now it's kind of automated here, but OSS, for example, will have a different model than Qwen. And Qwen, you'll use a different chat template if you're including reasoning or not. So you need to be careful with that. The response tag we're using, because it's not reasoning, it's going to be like this. So you're going to see in the template, there's empty think tags because there's no thinking. And that's the format for Qwen without thinking. All right, so we prep everything. I like to print out an example here. You can see the system, the user message, the grids. You can see the assistant's response. This is the labels. These are the labels here we want to train on. And then you can check if the masking works. And it does work because you can see it's masked everything out before the program. So this looks good. And then we're going to train. And yeah, I guess the training was really fast because we only trained for 128 rows. And we have a batch size of 8 per device. So that's going to be really fast because it means it's going to be 128 over 8, which is 16, I think. So it's only 16. Yeah, I guess then with gradient checkpointing as well turned on. Anyway, you can see here the training has proceeded. I can show you some training from earlier. I ran it with all of the data from that reasoning set. So let's take a look at what that looks like. I need to find my projects. I'm still a bit slow at navigating through weights and biases. I go to projects. I think I can find some. Yeah, here we go. So we'll actually see the run we just did, and we'll see the run I did earlier. All right. So here's the training loss. The training loss goes down. This is when you run the full data set. It's probably still going down at the end. You can see here it's running for 2 epochs, and there's this little discontinuity when you move from one epoch to the next. The learning rate is a ramp with a cosine decay, although we did just sometimes do flat linear, which I think is more straightforward, to be honest, and I think probably is the better option if you want to keep things simple. The grad norm falls down to below 1, so everything is pretty stable. You can also see the eval loss from that split is improving. Now, I remember it's not happening here, but I remember there were cases where the eval loss might go up, but the performance might still improve. Generally, training for longer we found better. So don't just rely on the eval loss, but if this is going crazy, that's a sign there's something wrong. And then the model will be pushed up. It's going to be the last checkpoint because that's what we set. But the model, the lower adapters will be merged onto the base model, and then they'll be pushed up to hub. Let's see if we can see where they got pushed. If I go to, can I just go? Yeah, looks like here we pushed up this test model. It will push up the trainer, and then it will push up a merge checkpoint. The trainer will have the optimizer states, and it will have the checkpoints, so you can continue training. And then it will also push up the merged final checkpoints. For example, this one here I pushed up earlier. So now you can grab this, and in the same way that we ran inference earlier, you can just pass that Hugging Face model, and you would just pass it in right here. So replace that. And then you could run, and it's going to automatically boot up a pod, install sglang, download the model, and then run inference on it. And yeah, I guess we can go back and look at maybe some of the results from our inference earlier. So remember, this was looking at 10 tasks, 10 evaluation tasks from ArcAGI 1 using GPT-5 Nano. And when it's given 4 attempts, it's getting 10% correct on a pass of 2 basis. It's getting 20% correct considering only the training examples, and 3 out of 10 tasks it's able to reach at least one of the training examples. Now it looks like it has not just written code, but correctly executed code that's executable in each case. So that's good. And yeah, 2.5% of the time, it didn't even give a program. And this is where you see a problem with OSS. If you try and run OSS, particularly on ArcAGI2, this percentage should be really high, like 50% of the attempts don't even generate programs. So there's a few stage gates. The LLM has to create the right syntax with the dash, 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 Python and then the code so you can actually extract it. Then the code has to be runnable. And then not only does the code have to be runnable, but it has to produce valid grids. By valid, we mean 30 by 30 or smaller with numbers 0 to 9. If it has anything else, then it's invalid. And then you only look at whether there is correctness on any of the grids. All right. So here you can see SGLang. This is the Qwen 14B SOAR model in FP8 format. Some nice throughput for a 14B model, about 2,500 tokens per second on just one H100. And there are 25 requests happening here. There are none queued up by SGLang. We're using not that much of the possible KV cache space. And let's see how far we're progressing. Okay, I mean, this is going to take longer than the live stream, but we've got about 14,000 out of 64,000. I can just do a quick search here. For example, this task here, it's getting 35 tests perfect, 22 train perfect. So it definitely has some tasks it's getting fully correct. And then it's got some, I mean, yeah, looks like it's got quite a few that it's getting correct here. Can't remember what data split I ran that on. Looks like I ran it on training. Yeah, so actually this is kind of silly that I did that because it's been trained on some of these tasks already because ArcPrize 2025 includes training. Be more interesting to run it on evaluation. That actually wouldn't be interesting though, because it's going to get very few of those correct. It'll probably get like 1% correct if you look at the evaluation split for ArcAGI2. I mean, we got 1.67 when we submitted the Kaggle, so maybe around 1 to 3%. But basically, it was really hard to get beyond that. I don't think we saw any tuned model that was able to get beyond that on ArcAGI2. So yeah, I've shown at this point how to train. I've shown how to run the evaluation. So you have all the tools. Let me know questions here in the chat because we've only got about another few minutes left. The last thing I want to show you is how to create some manual problems. And for this, you can go to experimental. And let's see if I can remember. Then you want to go to, yeah, just go to experimental and there's a HTML file here. So I'm going to copy the relative path. And I'm just going to open that. Okay. So this is a little thing I vibe coded, and it allows you to create some custom tasks and save the tasks. So I'll show you some of the tasks here that I've saved. This task here, let's actually grab that ID and let's go to my experimental notes, which some of you, I don't know, if you're really into it, you might want to read some of my only medium organized experimental notes. It's in the LLM Python folder, which I'll just share now. So yeah, if you go to LLM Python and then you go to experiment notes, you'll see a bunch of notes on different things that we tried. But at one point, what I did was I said, well, we can't teach the model how to do these really hard ArcAGI2 eval problems. So tasks, can we instead make some manual versions that are a bit easier and train it on those and see if that somehow transfers or builds into solving the harder ones? Or maybe even our dream was we would make some easier tasks and then compound them and train on the compounded versions and see if that would help generalize. Generally, I wouldn't say we tested it nearly enough, but we weren't able to get progress on that. But my idea anyway was to take an original task, which I'm going to show you here by going to play. So here's an original task. And hope I can do this on the spot. Not solve the problem, but explain what I'm doing. So this is an assembly task. You have a bunch of objects here, and you need to assemble it into a smaller thing. So you can see the blue is assembled in the middle, the yellows are assembled on the side, and then the magenta is assembled there. And so I want to make some tasks that are assembly, but they are easier. So this is my attempt. Now maybe you can see here's a yellow, here's an orange, assemble it into this. Here's a gray, here's a magenta, assemble it into this, and then some test pairs. So you can see what I'm doing. I'm making some easier versions of the tasks. And yeah, I did that with quite a few tasks. Well, not a whole lot, but about 23, I think. And you can make them too. You can just edit, pick a color, do something like this, put in some colors. You can also use fill if you want to fill, a solid color like this. You can also clear the tasks if you want to do that. You can also copy the input to output. So if you have an input like this, you can copy the output here. And then you can either update the task or view a saved task. You can also export them, which is important. So if you view saved, you can download the training examples. And after you download, you need to download the examples file and the challenges and the solutions file. Then you can use UV run experimental move downloads, and this will move them into data/manual. So it will move them into the data sets folder where you can then run evaluation or fine tuning or whatever the case may be. Well, evaluation really. So you can see they're being moved into this folder here. And then, yeah, I've created some subsets. So if you wanted, you can play around with some of these manual tasks here. All right, that's what I wanted to cover. You can find the repo on GitHub, Trials Research ArcAGI 2025. I've given you the fine-tuning tools, the evaluation tools. They're the main things. There's kind of a lot of other stuff in the repo that is best explored with Cloud Code or Codex. You've got that tool for making new tasks. And thanks to RunPod for support for compute. I've got a link in the description if you're looking on YouTube, if you want to get some kind of sign-up bonus. If you want to use RunPod, I really appreciate the support they gave for this. And that kind of rounds up ARC prize for 2025. There's still a month to go to wait on the official scores, which is kind of crazy. But I wanted to get out the approaches that we have taken. So you've got the video from yesterday on TRM. That paper is now published on Archive, so you can find it there. It's on X. I've also linked it on the ArcAGI page for Trellis. And then there's the blog talking about the Python approaches here, which talks a bit more about things I didn't even cover on this live stream. And that's it, folks. Thanks everyone for joining. I appreciate it.